Welcome back to Demystify Sci. I'm Shiloh.
I'm Anastasia.
Today we're talking cosmology with Martín Lopez Corredoira, who is an astronomer in Tenerife at the IAC, and he spent his career equally divided between the philosophy of physics and actual observational tests of standard model cosmology. And so this has been a really cool opportunity for us because, as many of you know, we are planning an Alternatives to Cosmology conference in Portugal. And of course, we would love to see you guys there, but we also want to go into it understanding very well the state of the art in cosmology. And we've been trying to find some folks who are experts in mainstream cosmology, perhaps to attend the conference to sort of bolster out and respond to a number of the speakers who are quite critical of standard model cosmology. So, Martín is a fantastic voice because he doesn't really cultivate his own cosmological theories so much as he studies the proliferation of cosmological theories and compares them against the data itself. This is a really cool opportunity for us to see what the holes in cosmology are, what some of the promising features of the alternatives have been across the past few decades, and to consider what are the features of the structures, the institutional structures that are perhaps holding us back from making progress, because there are a number of serious contradictions that we're facing in cosmology, particularly with the new James Webb Telescope data. We get into all of that and more. It's a really cool conversation. I think you're going to love it.
If you enjoy what we do on the podcast, consider coming over to patreon.com to support the show. Like I've said before on the podcast, we really depend on your support because we believe that it is necessary and important to produce intellectual content for the world without plastering ads upon it. And this is kind of the basis upon which the public universities also operated, which is that they were not for-profit institutions that had their own endowments and were out there trying to play the stock market to make a quick buck or whatever. And obviously, that has changed. I think Columbia has like a $10 billion endowment at this point.
Western society has become exhausted.
Yeah, and has turned everything into a business. And so we're experimenting. We're trying to make this into something that is able to run under its own support. So that means you guys, because you are the pillars of this community, you are the pillars of this show. We're just the avatars that happen to be here that are hosting the conversations. And so if you like what we do, and if you believe in the project, come over to patreon.com/demystifysci and sign up to give us $1, $2, $3, or $1 million a month. We will appreciate all denominations of currency. And we'd get to see you at our weekly patron chat. And you get to watch those videos from behind the scenes if you decide not to come to the chat, but they're part of the things that we offer patrons. You get our episodes early, you get them both on Saturdays each week. And in general, you just get to support the thing that you love, which I think is really valuable.
And if you want to become a patron later, but you can't afford it today, that's totally cool. Just share the podcast with somebody you think would love it. There's an episode that you come across and you know a guy at work who would be into it. Tell him about it. This is entirely how we grow and how we're able to reach out to bigger and bigger guests is by building this audience. So share the podcast. That's cheap and easy. You can also talk to us in the comments section. Come over to Discord, come over to Facebook, hang out, give us your thoughts, and we'd love to hear from you. It's totally free.
And we're planning our conference for June of 2025. It's going to be in Portugal. We're going to have a really, really cool long weekend from the 12th to the 16th at originally it was going to be a medieval village, but that has changed. And now I think we're going to be on the beach. So we're going to spend 4 days on the beach in Portugal talking about science, talking about cosmology, swimming, avoiding getting eaten by sharks, hopefully. I know Shiloh's very concerned, but it should be really fun.
All right, guys, enjoy this conversation. Tell us your thoughts. We'll see you next time.
The scientific revolution starts now.
Demystify Sci podcast.
Let us see in the dark.
The Big Bang seems to have gotten a lot of support out of the gate, and as it plowed along, like, we can make the case that as soon as the microwave background was discovered, it was almost immediately attributed to having this cosmic significance in terms of the Big Bang. And that's a really unique situation. Like you said, we notice things about the fossil overlap between continents for 100 years before people actually got on board with the continental drift idea. But this seems to have been sort of shoehorned in very easily. And I wonder if that isn't because the story of the Big Bang is a story that is congruent with the one humans have been telling themselves for tens of thousands of years, which is this birth of existence, the egg birth of the this is in so many different cultures that are separated by space and time from one another. Everybody comes up with this same, not the details of it, but the same basic story of this kind of boom thing where everything just pops into existence one day. It's very congruent with the creation story. And I wonder if that's to some extent why it's been so difficult to tell a different story.
Well, there are several points. About medicine is not my field, but I have read some papers from other colleagues, and I think there are similarities in some aspects of what happened in some areas of medicine related with alternative medicine, for instance, and the publications of ideas in the serious Western journals. I think there are some similarities, but it's not my field. I can just tell that there are something similar. The technical part is not. There are technical parts also in cosmology. Not everything is something philosophical, purely speculative. Of course. Cosmology throughout the centuries, if you go to the ancient civilizations, it was something more closer to philosophy or even religion, was part of our culture. Nowadays, the modern cosmology after the 20th century, tries to be scientific, not totally, because there are elements we have to speculate. For instance, we have to speculate that the laws of physics at the beginning of the universe are the same ones that we have nowadays. We don't have any proof that the laws are the same. We just suppose like that, or that the homogeneous principle, the cosmological principle, that the universe is the same from every point you observe. There are some principles which are I would say gratuitous. They are not demonstrated. They just posit these principles and they develop the cosmology. Nonetheless, once you accept these principles and once you interpret the data, because we have telescopes, we have invisible and near-infrared, X-ray, radio, microwave. Once we collect the data and we make the interpretation of the data, well, there is a technical part. It's not purely speculation. So there are both things. There are things that we have to speculate because we don't know everything. We have to assume something that we don't see about the dark matter, the dark energy, the inflation, many elements that are introduced ad hoc, usually in cosmology, in order to continue our way. But there are many technical things. Talking about the cosmic microwave background radiation that you mentioned, it's true that this was an important point in our history and our recent history in which most of the scientists moved to the standard theory in the 60s. There was another moment, perhaps in the end of the 90s, in which it was even also quite important with the introduction of the dark energy, the supernova, and even it was consecrated with a Nobel Prize in the 2011 to Adam Rees and collaborators. So there were 2 or 3 moments which were very important in the support of the standard theory. But one of them, perhaps the most important one, was the one in the 60s in which there were some a priori predictions. Somebody told, okay, if we have a Big Bang, we should observe a background radiation. This was predicted by Gamow in the end of the 40s, beginning of the 50s. And then in the 60s, 1965, more or less, there were some observations and they confirmed that exactly there was this radiation. And even the radiation has a black body shape as was predicted by the Big Bang theory. This is the part that everybody knows, and this is why people attach so much to the standard theory. They say, oh, it's wonderful. We have a prediction. We confirm this prediction. This can only be interpreted in one way. This model is correct. However, people usually do not tell the things that were not correct in the prediction, because there were many elements which were wrong also. For instance, the temperature of this radiation was predicted to be much, much higher than was later discovered. Nowadays, we know that the temperature of this radiation is around 2.7 Kelvin, the temperature of the radiation. The predictions were giving numbers much larger. Even Gamow, one of the authors of the Big Bang idea, and perhaps the father of the Big Bang idea in the 40s, Gamow was giving numbers as high as 50 Kelvin. 50 Kelvin. You can say that, well, it's not so much the difference between, it's only one order of magnitude, but we should remember that the energy associated to a radiation is proportional to the temperature up to the fourth power. So an error in a factor of 10 means an error in a factor of 10,000 in the energy of the radiation. So it was totally wrong, the predictions of this energy. This radiation has a much lower energy than predicted. This was one example of a failure in the prediction. The following one will come a little bit later, at the end of the 60s, and at the beginning of the 70s, it was a very precise prediction that once the radiation was discovered, it was expected to have some fluctuations of this radiation. The radiation was coming isotropic, in first order was isotropic, coming from all the directions. There was a contribution from the motion of the Earth, which is called the dipole. This is already well known, but there were predictions for the rest of the fluctuations, and this was associated with the seeds of the future galaxies, because in the Big Bang there is the idea that the fluctuations of this cosmic microwave radiation is what gives birth to the future galaxies and the large-scale structure. So the numbers could be calculated in the 60s, Sachs and Wolf and these theoreticians, and they predicted that the fluctuations were of the order of 100 in temperature. So if the temperature is 2.7 Kelvin, the fluctuation should be 2.7 divided by 100 or a few hundreds. The fluctuations were of the order of 100 lower than the main temperature. During the 70s, many observers tried to find these fluctuations, and they failed. These fluctuations have not been found. So this was the reason why cosmologists, in order to save the theory, because this will be a confirmation that the theory was not working in the 70s. Instead of replacing the theory, instead of saying, okay, this means that the idea, the Gamow theory, the Big Bang theory, as we know, is wrong. Instead of doing that, they have introduced the concept of non-baryonic dark matter, which is some kind of matter in which the photons do not interact with the normal matter. And this may justify that these fluctuations of the CMB are much, much lower than 100 as was predicted. As it is well known,
But isn't that just saying that we have a theory that predicts fluctuations and we can't find the fluctuations? So that means the fluctuations are still there, but they're happening in a way that we can't detect?
The thing is that there is a prediction that there is some fluctuations of the order 100. They are not found. So there are very sensitive detectors trying to find this fluctuation, and they were not found. So the only solution is modifying the theory, and this was introduced totally ad hoc. So it's something that was not predicted. This was the origin of the idea of non-baryonic dark matter. Much later,
it's interesting because it's not really modifying the theory, because the theory, if I understand correctly, the theory says that you should find the fluctuations. And so if you're saying that, hey, we've looked and we can't find the fluctuations, what you're doing is you're not modifying the theory, you're modifying reality. Because you're saying, no, the thing that we said that we would find is definitely there. We just our detectors just can't detect it because it's some new and exotic form of the change that we didn't expect to find. Do you know what I mean? Because like if the theory had predicted that, hey, there's fluctuations, but we're not going to be able to see them until we build a detector that's able to interact with non-baryonic matter, then you could say that, you look, you don't find anything, and the theory still holds without needing to be modified.
Yeah, like what would it take to falsify the Big Bang? Because this Popperian idea that we use in biology all the time, where you test your hypothesis, and if it's wrong, then the theory's wrong, and you got to come up with a new theory.
It's interesting to talk about this in this form because as we talk, I realize that almost no science does this. Like, getting rid of a theory is almost impossible in any branch of science. Like, I feel like we've just ground to a halt over the course of the last 40 years in most branches of science where there hasn't been huge theoretical turnovers. And so it's kind of funny. But yeah, I think Shiloh's right. What would it take?
Just to let me finish the story. The thing is that the fluctuations were discovered later in the 90s with the COVID data, and they were much smaller. This is what was the end, and everybody was happy because the fluctuations were much smaller, and now with the new element, you amplify the theory, and then with this amplification of the theory, you can explain the data. Coming to the question, the philosophical question, whether theories die or never die, my impression is what you have already said. It's very difficult to demonstrate, to falsify definitively one theory in these terms, because people will always find some new element trying to save the theory. This is the famous epicycles. No, we're talking about the geocentric idea. Okay, we have a new motion of the planet, but we can introduce a new epicycle, a new different or whatever, and we can save the theory. This is continually happening in biology, in physics, everywhere. The one physicist, very famous, called Max Planck, uses to say seriously that theories never die. What die are the people who propose these theories. The only way to bury a theory, to make the end of a theory, is that the people who are proposing this theory stop to do research or they die, and the next generations are educated in a new background of ideas and they change their mentality. But it's very difficult to convince a person that have invested the whole life in one theory that this person is wrong. There is no way. We have to wait some social change, that the power, the money goes to different directions, and the new generations, possibly in 20, 30, 50 or 100 years, the new generations with the new evidences will have new thoughts and they will support the new ideas.
Especially if you're giving Nobel Prizes to people for their ideas, it's going to be very hard to say, well, maybe there's something else going on here.
Totally right.
And I think that it was probably a lot easier when you could get every single physicist in a room together and have them be the world's top physicists to have a single funeral change the course of events. But now when you have these massive dynasties and institutional preferences, and right, because it's like, it's no longer a guy at Cambridge who's saying that, we have the Big Bang is the best possible theory. You have these massive continental institutions where every single person who gets funding to go there and to train with them is now being inculcated with it. And so in order for the idea to die, the whole institution has to fall apart, because that's now the body that is sending forth what the training materials look like, even if it's not explicit, right?
Totally in agreement. Yes, it's how it works nowadays. And the sad part of this is for the young generation nowadays, I think, because now a young researcher is in some way is motivated to continue the mainstream always, because they need economical support. If you want to get a new postdoc, a new PhD, you cannot start to develop some alternative ideas or to go in a direction that is not supported by the mainstream community, because you lose your opportunity to get your work. this is a circle, no? Because and this new generation, when they spend their lives after 20 years working in this line of research, it's very difficult. They go back. It's very difficult. They say, okay, now I have my permanent position. I can have my free time to do whatever I want with my research. It's very difficult because they have already been somewhat brainwashed. No, just not literally, but I mean they are educated in a direction, and it's very difficult. Not now suddenly after 20 or 30 years doing a mainstream ideas research, they change suddenly to another. There are exceptions anyway, of course. There are a few exceptions, but it's not the most common thing. These are some of the explanations why nowadays we have not many alternative ideas in the mass media. I mean, of course, there are alternative ideas, but I mean in the most visible places.
It's interesting to me that even the alternative ideas that you present still take the institutional assumptions at the heart of the cosmological theorizing on their face. And this might sound kind of crazy, so bear with me, but there's two really big assumptions in all of this work. One of them that everybody just takes for granted is that there must be a beginning to existence, which is a pretty wild assumption if you think about it, that all of existence could just pop into being at some point. And everybody kind of takes that on its face. So even the alternatives that we've been dancing around are trying to come up with different stories maybe for how things went down at the beginning, but they still assume a beginning, which I think is really, it's a big assumption, first of all. It's surprising to me that the null assumption isn't that there wasn't a beginning. Like that seems like it should be the default to me. And I'd like to hear your thoughts on that. The other one is that this plasma recombination moment, in other words, that plasma itself could even give you a black body spectrum, which could be responsible for the microwave background, has never been demonstrated on Earth. Like you can't get a black body spectrum from a plasma on Earth. And so that's a really weird assumption too, that you could get a temperature from a black body spectrum that was some way indicative of primordial atoms. Doesn't really hold up experimentally under scrutiny. So, but all of these different alternatives seem to take both those points on their face, which is just really bizarre. And I think that's speaking to what Anastasia was saying about this institutionalization of the approach, which is like, if you want to study these, even if you want to come up with alternatives, you got to at least be on the train to some extent with respect to the main pillars of the exploration.
Well, of course, astronomy is a very special science in the sense that we cannot make experiments on the Earth. I remember some teachers and lecturers that I was going to some classes some years ago and said that astronomy is the science of watching but not touching. I mean, they say everything is far. This makes a difference because you cannot reproduce the experiments as we can do in many other science. It's not unique. Maybe we can compare with the paleontology, for instance, when we study the conditions in the Earth, the primitive Earth. We only have the fossils, but we cannot go to the beginning of the creation of the life in the Earth. We cannot reproduce that. Not so far as I know. You know more about biology than me, but
well, at least we know there was life there, right?
There was life. This is true, but we cannot say, okay, we know how life was produced because I go now to the laboratory and I can reproduce the same thing. Yes, and we know that there is a cosmic microwave background radiation and there are galaxies and so on, but everything is theoretical and we have some models, but we cannot test.
Well, we know we know there's a microwave background. I don't know about whether we know it's cosmic or not. That's an assumption as far as I can tell.
That's an assumption. You are right. The other question about whether there is a beginning of the universe. Well, not all the cosmological models accept there is a beginning. There are some models without any beginning. The one that I mentioned before, the steady-state cosmology or quasi-steady-state cosmology, is an eternal universe. There is no beginning because there are many creations. There are many cycles of creations. and it's a continuous creation of matter. Rather than one unique moment in the universe in which there is one Big Bang, there is a continuous Big Bang. It's a continuous creation, and there is the universe was.
And it's fascinating that the only thing that seems to have swayed people away from that is the microwave background argument, right? I think it's quite fascinating that most people coming up today probably aren't aware of the steady state cosmological ideas, especially them being taken really fairly seriously, all the way up through the 80s, it seems like, maybe even into the 90s, and that the real point that sways people away from it is the interpretation of this microwave background radiation, which is just fascinating that one point could be the splitter of the vote like that.
Well, as a matter of fact, they offer some explanation, but the question is that the people was not convinced by this explanation. Hoyle and collaborators have proposed that there are some particles in the intergalactic medium. They call it wrinkles. Whiskers. These long needles of dust, very long, that are able to thermalize the radiation coming from the stars, the stellar radiation. They thermalize and they convert into a black body. This was their explanation for the CMB, and according to them, the CMB is being produced much closer to us than is proposed by the standard theory. But there are many problems. I agree that it's not so simple, because you just making a perfect black body we don't know any particle which is able to do that. Nobody has observed these whiskers or these particles, these needles. It's just a purely speculative particle, and moreover, we don't know how to combine the black body producing a different redshift to give place to a single black body. So the combination of many black bodies with different redshifts is not a black body, and this was not very well explained by the theorist. So I agree, there are many problems in the alternative explanations of the CMB. However, there are attempts to make explanations. Most people just do not listen to this explanation. They say, no, I don't. I believe the CMB is at the redshift 1100, and this is the reality. The rest, I'm not interested. It's not a question of discussing the physical ideas, what is working or not. See, the problem is simply that after some period, and you mentioned the 90s, this was the period in which the authors produced this explanation for the CMB. In the 90s, people were focused in the mainstream ideas, and any other idea was simply ignored, not even replied. Of course, there are problems to solve, but it needs more time to give a criticism and to reply, and just to check whether it works or not, the idea. And most of the cosmologists, most young generation don't even know about this idea. They don't know. The old cosmologists, they know, because when they were young, maybe they have heard about these ideas, but most of them, they have not spent not even 1 hour just to read one of these papers. They simply ignore them because it's not their work.
That's a really weird aspect of all of institutional science training, from what I can tell. It seems to be the same in almost every field, that there's very little time cut off in the education towards understanding the history of the ideas that are taken as baseline assumptions.
Well, it's kind of assumed that the ideas that we have now are the correct ideas. And so why would you go back in time and start to study the ideas that were defeated? Like, why learn about things that are wrong? I think is the attitude.
Yeah, it's like that. It's something pragmatic. Science nowadays has become something pragmatic. It's not something idealistic in which we are searching the truth. We are like philosophers with plenty of time, and we have infinite time just to discuss ideas. It's not like this. Now people is very busy. The science is a business, and in order to continue with this business, you have to produce more papers, you have to organize conferences, you have to have students, and you are occupied. You have occupied your time with many tasks. Many of them are not scientific tasks, many administrative tasks also, but people is occupied with that. So when
Isn't it crazy to think about how at the turn of the century, if you think about the 1920s Solvay conference, not a single person there was preoccupied with the administration of a grad student program or the fulfillment.
Federal grants.
Yeah, like all of these ideas that we place at the heart of science, from special relativity to quantum mechanics to just modern physics as a whole, all came from people that were part of a community, but were not doing anything except for theorizing about what the universe might look like. And so it's wild to think that the basis for our science came from people like that, as opposed to this massive institutional agglomeration that's just churning out papers and postdocs and everything else. Yeah, it's kind of frightening, because ideally you'd have a situation that you could get out of, like where you can see a path forward. But you were saying, if you're not institutionally affiliated, for a long time it was very hard to publish papers that had any kind of alternative perspective. And most of the people in the institutions...
Or papers at all.
Yeah.
Even if you want to go along with the ride, it's very difficult to publish without institutional affiliation. You have to build up a really careful reputation through collaborations and so forth.
Fair enough. And so do you see this changing? Do you see that now there's people that are challenging the interpretation of the CMB, people that are challenging the interpretation of the redshift, people that are challenging the interpretation of the expanding universe? Or are these pillars still unassailable?
There are very few people challenging all these ideas. Many of them are not in the most visible position. I will say they are a minority. Maybe I will say less than 1% of the cosmologists nowadays are trying to do that, and they are not the most famous ones. So possibly we will not realize of what they are doing, because they publish in minor journals, in dark journals. They don't go to the conference, or if they go to a conference, they present something very small, a small poster that nobody pays attention to it. So they are not in the visible way. I totally agree. I absolutely agree your point of view that science at the beginning of 20th century, the Solvay conference, and science nowadays are totally different ways of producing science. We have to realize, first, the number of people were much, much lower. We are now millions of scientists around the world in doing fundamental science. Only about astrophysics, which is a very small field, there are many tens of thousands of researchers, and there is a huge amount of money, and it's a business. Science nowadays has become like an industry. We are producing industrial science. It's not something like in which you are an artist mentality, in which you are more like a philosopher, thinking in your ideas and discuss from time to time with your colleagues some ideas. No, it's not like that. We have to understand science nowadays like a business. If you understand this, you will understand why people focus in what they have to attend. They have no time, because their goal is not just finding new truth. Their goal is just getting a new grant or a new project to have a lot of students. This is the motivation of the most relevant part of the scientists nowadays. The people who have the money, the people who have the resources. Of course, there are exceptions, and I know many of them. I'm in contact with many heterodox cosmologists, both professional, dedicated to astrophysics. Others are not embedded in the profession, but they dedicate a lot of time. And I know they exist. There are people thinking about that, but usually they are neglected. Why they are neglected? There are many explanations. First, I have to speak also about myself. We have no time to attend all the thousands of proposals that are everywhere. There are hundreds and hundreds of amateurs, or even not so amateurs. Some of them have education in science or engineer or whatever, and they try to produce new ideas, but they don't follow the usual mechanisms to produce science. They just stay at home, they write some paper, and they decide to submit by email to some colleague. And usually people has no time to pay attention to new theories, especially when you receive every year. In my case, for instance, I think I receive every month, I receive some email of some new idea of the universe, and I have no time to attend to all this because I have also my duties, my obligations. Usually, I try to reply everybody, and I try to give some advices just to where to find some discussion of these ideas. But most people, not me, but other people, even they don't reply these emails because we are saturated. We are too many, and there are many people making noise. And now with the social nets and with the YouTube and everything, everybody thinks that they can produce ideas about science even without formation, which is a totally wrong idea. Having formation in science is not philosophy, is not political ideas, religious ideas. In order to discuss some of these ideas, you need to spend a lot of years knowing some technical questions of science and reading a lot of literature of things. And the result is that nowadays we have a lot of noise, either produced by hundreds of barmies claiming everywhere that they have the absolute truth of a new idea of the universe that produce noise. And then there are few, which I know also very good professionals, trying to do really serious proposals of alternative ideas, but they don't get enough attention because they are mixed with the rest of the barmies. I mean, how can you distinguish among thousands and thousands of amateurs? How can you distinguish what is good and what is bad? No, your first reaction, I can imagine, if you are an editor of a journal or a organizer of a conference, your first reaction when you read in your abstract, there is no expansion of the universe or something, you don't continue reading. You close your article and you say, no, this is not the place for you. You even don't try to reject the arguments of the paper. Simply, if you see something that is alternative, you say, no, this is not, because nowadays there is so much noise with so many crazy ideas that people has no time to separate one thing from the other. We will need to create some jobs of people dedicated to pay attention to this theory, to read with attention, but this takes a long time because every time you receive a new theory, maybe you have to spend 1, 2, or 3 months just trying to understand everything and the origin of the formula, and people has no time. All this capitalist way of producing science nowadays, in this productive way that everything is measured in the number of papers, the number of citations, the number of conferences you attend, this is what is giving us a result that mainstream theories are successful and the rest usually are not paid attention. Yeah, we are not producing an innovative science because we try to give the answers before we have the confirmation, we have the data. Nowadays, the satellites, the telescopes, the space telescopes, the satellites are very, very expensive devices. And in order to get the money to produce this device, you have to convince other people and even politicians that the ideas that you have to produce this device are correct. So we don't build a telescope to confirm a theory. No, we build a telescope to sorry, I have not said correctly. We don't build a telescope to find new theories. Rather, we build telescopes to confirm that our theories are correct, because we write our projects 15 or 20 years before the space telescope is launched. We have to write the motivation and what you expect to see and what you don't expect to see. We have to convince many politicians and also people who are experts in science, but they are not researchers. They only worry about the economical questions. And in order to do that, you have to offer security in the science. Nowadays, science has become very conservative. Because if you give the impression that science is a place where everybody can discuss different ideas and like philosophers, and no idea is better than the other, with this impression, you don't get the money of the governments. Governments only bet their money for something secure. They want to hear, okay, you want this money to improve your theory, which is already correct. We know that this Big Bang theory is correct. Now you want to improve the accuracy to 1% to measure the cosmological parameters. That's very fine. Here you have the money. But imagine you say, no, I don't know which is the theory which is correct. You give me the money, and with the new data, we will see what we obtain from that. This is not an appropriate answer for people who is putting the money, because money always prefer the security, prefer that you are going to go to some direction, not some undetermined direction. You should say we need some hundreds of millions to find dark matter, for instance. We are convinced that dark matter exists, and in order to convince the politicians or the people responsible for the projects in science that you need to spend so much money for a new experiment to detect dark matter, you have to be sure that there is dark matter. If you have some doubts, you say maybe there is, maybe there is not. Well, just for having a game, people does not bet so much money.
Yeah, and if you spend $1 billion to build a telescope to confirm your theory, it's hard to imagine that you're not going to confirm the theory.
The $1 billion dark matter detector sure better find dark matter.
It will. It will.
I mean, I think that this is really tragic on one level, but on another level, it's possible to look at the situation and say, well, they are building the telescopes, and the telescope data is to some degree available. And so if there is a significantly large contingent of scientists that want to take the data that's being gathered and use it in order to make the case for their theory, surely that should be possible.
It's true.
Are people doing that, or does it just take too much time where they're
No, this is the good part. The good part is that these telescopes are so expensive that they cannot be private. They have to be financed with public money. And the condition with public money is that they should be publicly available. You cannot say, oh, these data are mine. I will not share with anybody. So this is the good part of the science nowadays, that the data are there and everybody can use to check their own ideas. Possibly you will not get the same attention, as I say, because it's not only a question who have the data. The data are available, but you can have the data, you can have your analysis, but you don't control the power in the science. There is a flow of power and money in science, like in any structure in the society. This is like politics. You have the appropriate contact among the mass media. Possibly you take your phone and you say, okay, I need somebody to write a paper in a major journal, in New York Times or whatever, that this fantastic discovery is going to make a revolution in science. And you get immediately a paper. But if some alternative idea cosmologist try to do the same, does not get the same reaction.
It's funny because one of those actually just called us. That was the phone call interruption, and he actually he had an alternative idea about cosmology, and he did publish it in the New York Times, but he had to actually take out a page as an advertisement to publish his paper in the New York Times, which is just really hilarious. Because it does reinforce what you're saying.
Money talks.
Money talks, yeah.
Money talks, yes. This is the reality nowadays, is that money is controlling the culture in general. Science, art, whatever you do, you are dominated by money flows. Those who have the money have the power to say this is the good science or not.
And it takes a lot of bravery, right? I think that's the problem. It's like Nasti was saying, that if you have a sufficiently large group of people that are willing to reconsider the data on its face differently, then yeah, you could. The data's there, right? The telescopes are there. They're generating massive piles of data. But the reality of the situation is that there's this principle of least action, where people are going to, for the most part, take a career and they have lives, they have children, they have to feed, like they have a whole existence that's very human. And at the end of the day, are they willing to really stick their neck out and fight for some idea that might jeopardize their entire livelihood and everything? It just seems absurd to expect large swaths of people to do that. Sure, there's going to be a few, but then they will be the black sheep that are easy to write off.
I have this other feeling, which is that perhaps it's absurd to expect that a life in science would be a fruitful and profitable one. Like, if I think about the scientists of the past, I feel like they were generally not very well rewarded from an external source. They might have come from rich families.
Almost always.
Almost always. You've got Gregor Mendel, who is a sinecure priest, and so there's this entire history of just like going to the monastery and living this very ascetic life and dedicating yourself to thought, which, even Darwin, right? Rich family, ends up on the HMS Beagle, comes back, and I don't think he works a day in his life in the sense of, getting all buttoned up and going to work in some office somewhere. The guy just thought. And so maybe there's this conflict between wanting to open science to many types of people and being able to get many different perspectives in on these questions that is in conflict with the fact that it is the grand autists of history that have produced the most interesting and fruitful ideas, where our desire to create science as a career, something that you can do with your life, where there's a ladder that you climb, has just...
It's pretty modern too, right? That seems to be a post-World War II situation for the most part, where you have the production of these giant institutions and career tracks for scientists, and even the peer review system seems to become an industry at that point. Like, it seems to be a relatively recent phenomenon. And I don't know if there's an alternative to that, but I do think there are really smart people working outside of the institutions that most people in the institutions would not be aware of. And that's a bit tragic.
And so I'm like, are they gathering together somewhere? Is there a place for all of the heterodox thinkers?
Next summer in Portugal, we will be making sure that happens, actually.
Yeah, but other than that, I'm like, is there a community for the heterodox thinkers where there's the 20, 30 best alternative cosmologists that are all coming together, or the top scientists from outside of the mainstream that are gathering, or that just doesn't exist yet?
I am a member of the Alternative Cosmology group. It's a group of that, and there are some professionals and others who are interested in the question. We are a few tens of researchers, so there are associations like this. The question, however, is the question of the publicity, the question of the money. There is not a specialized place where you can offer grants to people. So there is not a place where you say, here, our line of research is just investigating alternative ideas of cosmology. Yes, we have here some grant, you apply for it, and you get paid for that. No, this does not exist so far. There are many people. In my case, I can include myself some part of my time, and other people that have some staff position or some other kinds of research. And in some of this time, maybe 20 or 30% of the time, they dedicate to investigate some alternative ideas, but they are not paid to do that. In most of the cases, there are exceptions. Exceptions are, for instance, there are alternative ideas which are quite relatively successful nowadays. One of them is MOND, the modified Newtonian dynamics. This group, there are, I will say, several tens of researchers, professional researchers, doing this line, and there are many institutes with some departments in which there are some postdocs and PhD students working on that. So MOND will be one successful exception, but it's not a cosmological theory itself. It's only a particular solution for the problem of the dark matter. It's a competing theory with the dark matter, but not a general cosmological theory. However, coming back to the general case, in general, there is no support in general to investigate new ideas. It's very, very rare. You can do in your free time, you are not forbidden to do that, of course. In many institutes, you have some freedom to choose your own topic of research, and you do whatever you want. But however, if you want to hire some people in some topics, normally or never, I will say, you will find some offers of postdocs or some offers of positions just particularly to do investigation in these lines of research. Usually, they are ignored. No.
Seems like we're just one billionaire's foundation away from such an opportunity. Like if you go back to this, even the Solvay conference was set up by a rich guy who thought that it was important to bring all these physicists together. So it seems like it is possible, at least, if you had a billionaire who cared about these kind of things, which is perhaps unlikely.
I mean, almost certainly, but the thing that gets me is that it used to be that the wealthy were actually doing some of the research. Like it was the idly rich that were setting up
Tycho Brahe.
Yeah, there's a long tradition of the weirdly wealthy
Christian Huygens.
blue bloods doing. I mean, even I guess Newton wasn't terribly wealthy. But there's like a long tradition of the blue bloods getting fascinated with questions of nature and dedicating their lives to it in a way that's outside of any kind of institutional pathway. And I'm just perplexed that that doesn't seem to be the case anymore. Like, where are all of the strangely
I think the wealthy
rich
people
lords?
think that the institutions have it sewed up for the most part, you know? Like the wealthy people I've talked to just, or even anybody on the street just sort of takes it on its face, like the assumption level here that the Big Bang's been sewed up and there's just little dots and T's to cross and so
I don't
on.
totally buy that, even though I think that it's superficially apparent that that's the case. Because I'm like, there's a lot of alternative theorists.
I think we should unpack some of the alternatives that are, or the pieces of the alternatives that are attractive to you. But maybe we can take a short break and gather our thoughts a little bit, use the bathroom really quick, and then come back in 10 minutes to close this down.
Sure.
Excuse the interruption. I need to ask you to support this program if you're enjoying it. If you've made it this far in the podcasts, you've probably made it this far into many of them. And if you're at that point and you think you could give just a few dollars to help us keep the lights on and to put more and more of our time towards this project, come over to patreon.com/demystifysci and join our valued listener community. Really, come hang out with us. We get together once a week and tell us your thoughts while you're supporting the project. That's how we want to keep things going, and you can help us do it. So I'll see you there. Patreon.com/demystifysci.
So we've established that there is, in fact, a society for alternative cosmology. It is perhaps not made of the idly rich, as it was in the past, but there is a group of people that are pursuing these questions and are interested. And when we were on the break, Shiloh was saying that perhaps the most interesting direction to go from here is to see what these ideas are and what you think are the most promising ones, since you seem to have this survey perspective on the field.
As I said at the beginning, I have not any favorite alternative model. I try to avoid even any compromise with an idea, just because it is my work. I compare sometimes my work with the business of a lawyer. A lawyer is a professional in the law. He knows how to present a case, how to defend some customer, but can also defend the opposite arguments if necessary. He should not have any internal convictions. Sometimes, of course, he believes some version of the case, if there is any crime or any murder, and he may have some belief, but should act as there is no any belief. And in my case, I try to attach to this work of doing the things. I classify myself as skeptical of everything. So I'm skeptical of the standard model, of the mainstream. but I'm skeptical as well of the many alternative ideas. There are, of course, I agree that there are some ideas which are better than others. Not everything. This is not democratic. Not all the ideas are the same. There are people who have been creating some theories which is more consistent with the data, and it's very difficult to reject it because there are many elements to play with it, and it's not easy to reject. And there are, however, other ideas that you can reject immediately. Just somebody tells you, "Oh, this can be like this." No, this cannot work because this was already demonstrated many times 50 years ago that this is not working. So there are all these kinds of ideas. I think also, as I said before, we should be more humble as scientists, not trying to make a theory of everything. Cosmology is too ambitious. For me, it's enough just to understand the galaxy, the local universe, understanding some few processes, for instance, the cosmic microwave background radiation. It will be very interesting to have more information just to understand what is going there. At present, we are making some assumptions that you say, okay, this is the plasma, that is the recombination epoch at redshift 1100. But even nowadays, we have not direct information about the redshift of the cosmic microwave background radiation. This comes from the theory. Possibly in the future, there are already some future experiments, some plans for making some future observations to obtain some spectral lines of the cosmic microwave background radiation and obtain directly the information where this radiation comes from, rather than making the assumption. This will be an appropriate step in science. So for me, the more information you have, free of any prejudices, the better. Now, of course, we have the James Webb data. This is fantastic. It should be fantastic. It was the most expensive telescope ever, with several orders of magnitude more expensive than the usual instruments, and it should produce something much more incredible. And it's producing something amazing. So I don't know whether it was worth or not the money that it costed. It was huge. We are talking about $10 billion. I think it's a huge amount of money, but for sure is giving us a lot of information. This will take many years, many decades of many discussions just to how to interpret that. But this is the step to build our knowledge, just brick by brick. We are adding new information, and after having such a big amount of information, all the data, we have to give sense to interpret it. If we can produce with all this information something that is similar to a cosmological model, it will be very good. But my advice, my preferred direction is just the inductive method. First observe and then produce the theory, not the opposite. Now we have the problem that we have some galaxies at high redshift that we don't understand, that apparently they are too old for the epoch of the universe in which they are observed. Well, maybe we have to modify the cosmological model and to make a new cosmological model or an old one that allows galaxies to be much older at this redshift. So this is the thing. We cannot produce a happy idea, just a model that explains everything. We have to construct, we have to build step by step our knowledge and accommodate the knowledge to the data. Possibly people, especially people who are more Pythagorean, that think that the universe is pure mathematics and we can unify all the laws of physics, unification of physics, they think that just one simple, elegant idea will be able to explain everything. This would be fantastic, but the reality has demonstrated many times that this is not the case, that especially in things like astronomy, there are many elements to take into account. It's not only the cosmology. We have to understand the star formation history. We have to understand how the galaxies are formed, the mergers. There are many elements to take into account to build all this scenario. After many decades of studies, and I suppose the James Webb has been a very important contribution to that, possibly we will be a step closer to the reality, not the total truth, not the cosmology, just understanding everything. Possibly we will never reach this kind of delusion of grandeur, the cosmology that knows everything, that like reading the mind of God. No, this is not my idea of science. Science is just built with small steps, and we have limits of knowledge we have to recognize. Possibly there will be things that we will never know. We cannot visit the past in the universe. We cannot reproduce the many experiments that have been taking place putatively in the beginning of the universe. So possibly we have to just restrict ourselves to some few speculative hypotheses, but nothing else. We will not advance from that.
I wonder, maybe a better way of asking that question would have been, are there elements of the different alternative proposals that you find attractive? If not, obviously, there's no perfect theory to explain the data, but like there are some people trying to explain this new mature galaxy very early on phenomena. Like, do you know Raj Gupta at Ottawa?
Yes, I know. He has a proposal of a universe which is 26 billion years old. Yes, indeed, it's a combination of standard theory with other elements, with some kinds of direct light, and they are new free parameters. It's a way to fit some data, and it works in some aspects. Of course, I think he uses supernova and other maybe gamma ray bursts and other elements just to fit their model, but at present is just a toy model, I would say. It's not enough developed. It does not give explanation. There is not explanation of the CMB, for instance, so there are no explanations of, has not given so many details. And for instance, about the Gupta, I always have the doubt why we don't observe objects as old as 25 or 26 billion years old. Most of the galaxies are, as far as we know, maybe we will be with surprises in the future, but in our galaxy or in the nearby universe, most of the objects are around 13 billion years old, not more than that. So there are many things to solve. As I say, possibly Gupta has the basis of some development of some idea, but it's still a toy model. There are many questions open. I'm more enthusiastic, perhaps, with one model called RH equals CT, possibly somebody know, also called zero active mass. Is by one of my colleagues, is by Fulvio Meliá, American researcher, and some collaborators, who have produced a model which is very close to the standard model, but there are some different assumptions. He uses also general relativity. He uses Friedman equations there is expansion of the universe. There is a beginning of the universe. However, he makes the assumption of what he calls the zero active mass, which is some kind of equation of a state between the density and the pressure that should be the same throughout the history of the universe. It's called rho equals 3p or something like that, that the density and the pressure are related. And this is, with this condition, he is able to produce a universe that resembles very much to the conditions produced by the lambda CDM, but without introducing any new element. He does not need, for instance, dark energy. One of the things that is very amazing that he gets, only with this assumption, he gets a coincidence. In this model, the expansion of the universe is constant. There is no accelerated expansion of the universe. But there is one fact that has called my attention, that nowadays, in this moment, at redshift 0, we live in a universe in which the expansion and the deceleration of the universe compensate to each other. So it's like having a constant ratio. And this is not naturally explained in the standard model. It's just a coincidence. Why this? Why now? Why in the moment in which the both tensions are in the same are more or less of the same order? This is not explained as unless you suppose it as a coincidence. However, in this model by Fulvio Melia, the RH equals CT is something that comes natural. Just the equations predict that in any moment in the universe, the rate of expansion is the same, and because there is no accelerated expansion. So there are some difference. The age of the universe in this RH equals CT is a little bit larger than the age in the lambda CDM. Instead of 13.8 gigayears, is 14.5. This is a minor difference, but gives a little bit more space, more time for the galaxies to be created at the beginning. The difference comes especially at high redshift. So, for instance, when you go to redshift 8 in the lambda CDM means 600 megayears, the age of the universe. However, with this alternative model is 1.5 billion years, so 1,500 billion years. So you have much longer time to produce galaxies, and this will explain, for instance, why we observe massive galaxies and massive black holes already at very high redshift. This is just to put one example of some very interesting ideas that have been developed in the recent years, and possibly they can explain better, even than the lambda CDM, some particular problems. Nonetheless,
it's interesting. What was the highest redshift that was observed with the previous generation of telescope?
The previous generation, the most important one, was the Hubble Space Telescope, perhaps. And I think before the James Webb, we reached 9 or 10, more or less, or even 11. I remember there was some galaxy at redshift 11.
And then the highest with James Webb?
Now with the James Webb, confirmed spectroscopically is 14.
So like that just makes me think that if we just keep building better and better telescopes, we're going to just keep pushing the date back. Like, you know, sure. at its limit, if telescope generation corresponds to longer wavelength, if that trend persists, then at some point you need to just resign yourself to the fact that the redshift is as big as you want it, or as big as the budget that you have to build a telescope for.
Right. And if you ask me 20 or 30 years ago, the maximum redshift was around 5 or 6. So in 20 or 30 years, we have multiplied by 3 the maximum redshift of a galaxy. Is incredible. But this depends on the amount of money that you spend in building big instruments.
Hey, I have a question. Has the age of the universe also increased in line with the increased redshift? So you're saying that we've multiplied over the course of the last 30 years, redshift has gone from 5 to 6 to 14 or something?
No, the age of the universe of the standard model is derived from the theory directly, not from the observations. You have some free parameters, of course, depends on the free parameters. And the free parameters have been more or less the same in the last 25 years. The last big change in the free parameters was in the end of the 90s with the proposal of the dark energy. The dark energy has introduced a big change. And this, indeed, there was a problem. Before the dark energy, there was some tension because the universe was too young compared with the oldest objects observed with the globular clusters or others. But after the introduction of the dark energy, the omega lambda, the age was more or less, has become more or less stable, 13.7, 13.8, with now the accuracy with which we can determine is better because we can measure the parameters with more accuracy, but it's more or less the same. There were not such a change. However, as you said, the redshift of the galaxy that we can observe now is much higher than in the past. This is so now we can observe the universe when it was much younger than in the past. Redshift 5 or redshift 6. Redshift 6 is 1 gigayear. If you go to redshift 14, as I said, it's like maybe 300 or 400 mega years, more or less. So now we can go to the universe when it was 3 times younger than previously. And these are what is generating the problems, because there are surprises. In the past, we have built a theory based in our knowledge for the universe at redshift lower than 5 and 6, and we have extrapolated, and everything works perfectly. In the moment in which go to observe galaxies at much higher redshift, we find that things are not working so well. And possibly, if in the future somebody builds a new telescope, a new satellite, even better than the James Webb, difficult to imagine because it's so good, the James Webb, it will take a very long time to build something similar or much better than this. But maybe in 20, and 30, and 40 years, we will have something better. Possibly, we will have, again, new surprises, for sure.
Okay, so if they're not getting the age from the redshift, which seems to have changed over the last 30 years, can you tell me how they get the age from the model?
Simply from the cosmological parameters. Once there are many parameters in this, but the most basic ones from the standard cosmological model are 6 parameters. And these parameters are measured with the data, with the supernova, with gravitational lensing, with the cosmic microwave background radiation. The more information you have, the more precise you can determine these parameters. Now we have more precision than in the past. This is why we can determine with more precision. The error bars are smaller, but however, it's not so different. I mean, for instance, mainly the main parameter that determines, also other parameters take place, the omega m, omega lambda, but perhaps the most important one is the H naught, the Hubble constant. Nowadays, well, we are discussing, there are several groups, whether it is 67 or 74, there are some tensions, but this is the same value that was more or less measured 20 or 30 years ago. The only difference is now that the error bars are much smaller. In the past, we measured 70, maybe plus minus 5.
And they're different values, right? Depending on whether you look at the CMB versus the...
This is called the Hubble tension nowadays. There are 2 main groups in cosmology, one related to the cosmic microwave background radiation, and other related mainly to the supernova and Cepheids, and also you need to calibrate the supernova with Cepheids and other elements, but these are related with the observations of galaxies. And nowadays, they claim they have a tension. I mean, the value given by the cosmic microwave background radiation is around 67 plus minus 0.7, something like that. However, for the supernova, they claim it's 73 or 74 plus minus 1. So there is a 5 or 6 sigma tension. However, I have to add that, in my opinion, these error bars has to be better estimated. There may be some systematic errors. So, in other words, possibly some researchers are being very optimistic in the claim that they can determine the Hubble constant with 1% error. It's not clear. People who claim that these errors are correct and the measurements are perfect, they say that there is a problem either with the standard model or something that we don't understand in the physics, why the Hubble constant measures in different systems is different. However, there are possibilities, and it's not impossible, that these differences come from not taking into account some systematic errors in the way of measuring the things. For instance, maybe I explain you. In the cosmic microwave radiation, apart from measuring the radiation coming from the cosmology, from the decoupling matter radiation, there are many foreground contaminations coming from our own galaxy, coming from other galaxies too. So the technicians, the experts in this CMB, they need to subtract the contaminants. They claim they can do it perfectly. They claim, okay, we know perfectly how is the galaxy, the cirrus of the infrared cirrus of the galaxy. We extrapolate the emission in infrared, we subtract in microwave. They claim is perfect. However, and it is well known, once you do the correlation of the clean CMB maps with the galactic maps, either from our galaxy or other sources, still you find that there is some correlation. This means that your map is not totally clean. There are some residuals. And if there are some residuals, possibly the error bars with which you measure the cosmological parameters are larger than what you claim. So you are being too optimistic claiming that your map is totally clean of foregrounds. With the supernova, there are many other problems, because in order to know the distance, the relation of the distance and the luminosity of the supernova, you need to calibrate with phase, and there are many intermediate stages for making the calibrations. And also, there is something which is quite evident, and people know it. People know that it's a small problem, but they sometimes ignore, is that they are assuming that the supernova are all the same in the local universe and in the distant universe. They claim they are standard candles. This means this star has the same luminosity here and at the beginning of the universe. It's the same. This is not totally correct, I will say. This is an assumption. And if you make...
Well, they've been wildly wrong about that in the past, right? I believe that the first estimate with the Cepheids confused two different types, and they actually ended up having to change the age of the galaxy by like 2x. I forget who it was. I could look that up. But yeah, I don't know. Was it the Cepheids or... I think it was. I'm going to look this up. You guys talk amongst yourselves a second.
Indeed, well, it's very curious if one can follow the history of the measurements of the Hubble constant. Indeed, I have been doing some analysis of this. You can see that there were always some tensions. There were always, throughout the history, some different groups measuring different values. So it's not only a question that now in the 2020 or 2019 we have found a discrepancy between two groups. No, there were always some different groups, because there are different ways to measure, to calibrate the things. It's quite normal. During the 20th century, in the last 2 decades, in the 70s, 80s, 90s, there were two big groups using extragalactic astronomy. There were two groups, and one of them was measuring a value of 50, around 50, was the group of Sandage and Taman, very important astronomers. Sandage was a disciple of Hubble, for instance, was a very good tradition of a North American astronomer. And then there was the group of de Vaucouleurs, a French astronomer with a big group, and they measure a value of 90 or 100. And during 20 years, they were complaining to each other that the others were not doing correctly the measurements, because they were totally convinced that their values were correct. In the end, it was solved in some intermediate position. It's not 50, it's not 90, it's 70, it's something in the middle. And this was I would say, the consensus position. No? Now the people in extragalactic astronomy agree that it should be around 70. So the problem is now that we have different ways of measuring the cosmology with the CMB and with the supernova, and still we are finding that there are some discrepancies of 10%. But in my opinion, I will not give so much importance to this discrepancy, as it can be due to many systematic errors. I will even interpret these values within 10% as a success of the prediction, that rather that they are very similar. 67 and 74 are quite similar to each other. But of course, it's one of the hot topics nowadays in cosmology. How to solve the Hubble tension is one of them.
So I did look this up. It was Walter Beatty? Walter Beatty? Yeah. I guess they had confused originally classical and type 2 Cepheids, and this was leading to almost I think, half the age of the galaxy that they had originally, or actually they doubled the age of the galaxy as a result of this. My point is that there's ample precedent for confusing these standard candles, as you will, and the more that we learn about them, it could certainly reframe how we think about these systems in a dramatic way sometimes.
Yes, but as usual, all this information, what you have mentioned about Bade, what I have now told you about the discussion between Sandage, Antaman, and de Vaucouleurs, and this should teach us that the measurements in astronomy have many sources of errors. So we should not use one single measurement of few single measurements to support any revolution in science, to say, hey, here we have a number which is, instead of being 70 is 65. This means that everything has to be changed. No, before changing everything, before changing the cosmology or other things, we have to be very sure that the data are correctly analyzed. And sometimes things are not so easy. The theoreticians in physics sometimes do not realize of the difficulties in analyzing the astronomical data. They think it's very simple. They think it's like making an experiment in which you can get very accurate numbers in your laboratory without any external factors. But in astronomy, we have many external factors. We have many things to take into account for making corrections. And one of them, as I said, in my opinion, is that making the assumption that the supernova here and with some metallicity and some age is the same, that the supernova with different metallicity, with different age, and this is something that to investigate a little bit more. As a matter of fact, I have read some years ago some papers by some South Korean researchers, and according to them, they find that it's expected to find some variation of the luminosity of the supernova. So we should take all these results with a grain of salt, in both aspects, in the theory and in the observations. Observations are not totally trustworthy. We need to repeat and repeat again and until they stabilize. We should not trust just one observation 1 year that claims something fantastic. No, we need to repeat this observation many times until there is some kind of consensus. And the theory the same. We should not, just because you have a very elegant theory that predicts many things, maybe it's not a perfect theory. Maybe we need to correct, and maybe it's not the right one. This is science. Science is like this. Science is not security. If you want something secure, change your job or something. But science just is risk. We should associate science with risk. Without risk, it's like the English proverb, no pain, no gain. We need to take risks, and we need to make a lot of errors during many years in order to get some solid truth. And this has always been the same. Of course, science is produced nowadays in a different way, as we were discussing some minutes ago, with respect to the past, but the concept of science is the same. We still are not in a solid surface. We are navigating with many waves and many unknown elements.
I mean, I think that that's certainly true, and it's interesting to me because there's so many assumptions that are baked into the pie, right? So if we look at the Hubble constant, it gives us the age of the universe, provided that we assume linear expansion of the universe, right?
Well, in the standard model, there is no linear expansion. There is another one with linear expansion, but the lambda CDM, it has also the dark energy. There are other elements to make.
I see.
But yes, let's assume that at a first approximation is something like is inversely proportional to the Hubble constant. So the larger is the Hubble constant, the lower is the age of the universe, and the opposite. Not linear, but in some kind of relation, yes.
And so to the point that Shiloh was making earlier, which is that as our telescopes improve and as our ability to look out into the universe gets to be sharper and sharper, it seems reasonable that we'll start to see things that undermine our principles of uniformity, right? Like, because again, not an astronomer, but haven't we been finding structures that are really large in the universe that shouldn't be possible given the way that our current models are constructed right now?
Right, right. You know it. Yes, there are many claims. I have read also some papers of that. Nonetheless, I have to say now, if we go to the other side, that it's not so easy to analyze because these big structures sometimes have a very low overdensity. So it's not only the size of the structure, it's also the overdensity. If it is 20% over the average density or if it is 1%. So if it is a big structure with a big overdensity, this will be surprising. But many of these structures that you claim have a very low overdensity. And when you go to your simulations, it's sometimes, according to some experts, I'm not one of them, I'm not working with simulations, many people claim that they can reproduce even this big structure. So it's not, it's a question of statistics. It's a pure statistics. How probable is to find a structure of this size with this overdensity or underdensity in case of a void? Sometimes, even if just looking at the map is very surprising to have a structures of many gigaparsec. Sometimes when you compare with your simulation, you see that the probability is not negligible. Maybe by chance, there are random fluctuations. By chance, you can create these structures. But these things have to be analyzed one by one. We cannot generalize. We cannot say everything is correct, everything is wrong. No, we have to analyze. It's a matter of discussion. It's a topic of discussion. So there is no clear answer to this question. There are researchers that claim to have discovered big structures impossible to be reproduced. However, I have seen some replies of some Orthodox cosmologists claiming that with their simulations, they can reproduce that. Who is right, who is wrong? Well, yes, this is the thing. We have to still wait until this stabilizes again.
So there's a really interesting feature of biology, which is that we have this sense of the universality of biological principles, where everybody's got DNA, everybody's got RNA, everybody's got proteins, and that we're all produced off of this shared genetic code. And so we have a rooted tree that we can paint for the foundations of all of life on Earth. And then you go and you ask the question, you're like, well, okay, how many species on Earth have we really deeply investigated biochemically? How many genomes have we sequenced? How many creatures have we mapped their protein atlas? How many of them have we really traced their biological inner workings? And it turns out that it's like 0.02% of the known species on Earth have actually been investigated to great depth. And that's to some depth, right? To great depth, the degree to which we have predictable models for how you can use an E. coli cell in order to produce insulin or whatever, there's countable numbers of those kinds of experimental paradigms that are really, really solid. And so when I start to think about something as big as the universe, and I think about this teeny tiny little telescope that's sitting out there and is studying the universe, I'm like, how much have we looked at? It seems like even 0.02% is fantastically optimistic as a full survey of the sky.
Especially if the thing can only see as far as it can see, right? History would prove out that you're only seeing as far as your technology allows you to.
I'm like, let's say that it can see to the edge of the universe. Like, let's give them that assumption.
Telescope.
It's a perfect telescope. The James Webb is the perfect telescope. It sees to the edge of the universe. What percentage of the universe have we actually imaged?
Well, we don't observe the whole universe for the simple reason that there are some objects which are very faint that cannot be observed at high distance. When we say that we can reach redshift 14 or 15, this means for the brightest galaxies. But apart from these brightest galaxies, there are many dwarf galaxies with less massive that are not possible to be observed. Even if we go now in our galaxy, in the Milky Way, we are able to see many stars, even brown dwarfs, even planets in other stars. But if we go to Andromeda galaxy or other galaxies which are beyond, most of the objects cannot be observed because they are very faint. So, of course, there will be always a good part of the universe that cannot be observed. You can infer their existence, of course. You can calculate the mass and you can say, okay, here I cannot see all the stars, but I can calculate how many stars are there because you have the luminosity, you have the kinematical effect. There are many ways to calculate. And nowadays we have estimation of what is the content of the visible matter of the universe. Another question is the dark matter, because this is also it's more speculative, but about the visible matter, well, we can put some constraints. There are also, apart from stars, there is gas. Gas can be observed in radio, emits in radio, but when it is very cold, I mean very low temperatures, the emission is very low, so you cannot possibly you cannot observe it. So there is a good part of the universe that we don't see. We only see a small part. It's like an iceberg. You see maybe the 10% and the rest is under the sea. Well, in the universe also we are observing some more remarkable bright galaxies. We are following some structures in the large scale structure, and we are assuming that there is something else near this that we don't observe, but we can introduce in our calculations.
And so, I mean, I guess what I'm trying to get at is an order of magnitude approximation. Have we mapped 1/1000th of the universe? Have we mapped 1/10th of the universe? I know that this is kind of a coastline problem. I don't know if you know this,
so
where
you can
it's
only
like,
see as far as you can see.
but I was saying of
the end of
the
the day.
distance that we can see, like, because in my mind, I'm like, we have this patch on the far wall, like it's kind of like. Did you ever see the movie The Truman Show? Where Jim
Yes,
Carrey's right, and so
yeah,
like he gets to the wall at the edge of the sea, and then it turns out that there's a door in the wall, and so I'm imagining that we're like imaging that wall that's at the far side of the sea, and we have like a 2 by 2 foot square, approximately, on the back of that wall that we have imaged, and then you have the entire dome of the sky of the celestial plane that to us is just still completely unmapped. And so there might be weird things that are there that we haven't seen yet. There might be strange things that are happening right under our noses
That's something we didn't even talk about that I think is really fascinating, is the resolution upgrade with the new James Webb, like the impact that's having on our ideas of planetary formation and so forth, right? They have these pairs of super Jupiters orbiting one another with no star that they're detecting in the Orion Nebula, which is just absolutely fascinating. That you would have planetary systems without stars, I think was beyond people's conception until very recently. So
and that's
it's
kind of
also
what I mean.
like that close range but high resolution data that's coming in, which expands our universe.
Which is why it makes it kind of a coastline problem, right? Because it's like the question is like, okay, well, how do you measure the coastline? Do you approximate the shape of the bay by just going across the mouth of it? Do you have to go up the bay? If you go up the bay and there's a river delta, like, do you measure the entire river delta? And so at some point you come to a place where philosophically it's intractable to say how long the coastline actually is, because you're having to bound things. But what I'm trying to get at is just that it seems like our model of the universe is built on a vanishingly small set of observations, and we are extrapolating from those observations to universal principles. And I'm like, is that a fair process? Or are we setting ourselves up for eventual failure because we don't build in this humility into our models that says, like, hey, we've looked at this teeny tiny little window, and we can kind of make assumptions about what we've seen, and yet we know there are things that we haven't seen, and therefore we must be more careful.
Well, at the beginning of the creation of the cosmological model, it was like this. There were very few data, and many speculations. Indeed, when Hubble discovered the expansion, the redshift that was interpreted in terms of the expansion of the universe, and later when the Gamow tried to introduce the model, was just to explain few things like the abundance of the light elements, the existence of helium, why the helium is 24% of all the atoms in the universe. So, well, this kind of there were very few data only. Just the expansion of the universe, the elements, the light elements, and the local universe. This was in the 40s, in the 50s. After that, then the number of data have been increased. We have the CMB, we have the large-scale structure that now we can create maps. This was after the 70s and the 80s. We can create maps with 3D, because you have the distance, 3D maps. You can see the filaments and the buoys and all this. So all this is more information. However, the model was created before all this data became available. So instead of learning from the data, we are trying to adapt the data to our models, is what we are doing now. Instead of just having a white page, a white mind, you say, free of any prejudices and observing and trying to learn something from the universe, what we are doing is, here is the reality, which is my Big Bang model, and now bring me more data that is going to confirm my reality. This is somewhat disappointing, frustrating for some cosmologists, because it's not happening like this. Every time we have new data, they have new headache, because they have to think, and now I don't explain this new data, I have to do new things. No, frankly, I think we live in there are some positive things and negative things of our era in science. One of the most positive things is the amount of data we have available, the amount of instruments, the amount of computers, the databases are fantastic. And in the past, they have not so many instruments to develop the ideas in astronomy. They used more the imagination, the mathematics, the intelligence in some sense, but not so many data. Nowadays, we have too many data, and even we have not enough time or enough people, enough manpower to analyze all this data. Sometimes having too much information is not the best thing. Sometimes because people become distracted with many things. They don't focus in only one question. When you have few information, you try to make all your efforts to explain one single set of data. When you have hundreds and hundreds of data, and every year you are increasing more and more data, you are not finishing your analysis of data, and new data are produced, this kind of stress, this kind of anxiety just to be trying to understand the last data is not allowing people to take a rest, take a pause, and think slowly, because science overall should be about thinking and thinking slowly. And now we have too much pressure. This big amount of data do not let people think slowly, because every year we have increasing more and more data. Every year the computers are more and more are faster than in the past. So we need to be updating continuously with new information, and we are not able to absorb, to assimilate all this information. We need to have a more slow science, I would say. But this is my particular opinion. I suppose not all scientists think the same.
Yeah, I wonder if something parallel to the startup culture will rise up and replace these kind of concretized, ossified institutions, right? So this is a known problem in business as well, that companies might have a really good idea originally and they build their fame on the back of it and their brand up, but then they're no longer able to innovate because the institution of the company has gotten so big and complicated that it's very difficult to do new things. And so, obviously with Silicon Valley, I think there's all these startups that were popping up largely because there's very low investment capital necessary to get one of these companies off the ground. You don't have to buy any huge machines or anything for a lot of this stuff. So you can get a few people together and actually create a company that might have a brilliant idea, and they can take it off. And maybe it'll become a full-bloated institution at some point.
The brilliant idea getting funding is predicated on the fact that it's going to make somebody $1 billion. That's the only difference that I can see that complicates the situation, because I'm like, I don't know a model of astrophysics that's going to make anybody any money.
Well, this is an analogy, right? This isn't about, I'm making an analogy to the business world about money being an investment growth and all of this being the business world, whereas the success of your theory is in some sense the product of scientific labor, pure scientific labor, not like we're talking about pure science here. This stuff doesn't lead to new technology directly.
Yeah, and so I'm like, I think that the path that I see that's most likely, because for whatever reason, billionaires aren't funding this stuff. There's no Jeff Bezos of the world who's like, you know what, I'm just going to give basic scientists a bunch of money so that they can pursue their theories freely with no return on investment for the rest of their lives. For whatever reason, that's not happening. And so I'm like, I don't know if it can happen. But I can imagine a situation where there's a really vibrant community of people that are working together outside of the institutions to develop these ideas, which don't require a lot of money. Like you said, you don't need to have a ton of money in order to analyze James Webb data. You just need to have a group of people where you have the intellectual capital so that somebody can say, okay, this is the way that we actually access this data. This is the way that we parse the data. This is what we do with it once we have it. Because like the data sets are not trivially easy to access. Like you have to have some training and some expertise to even be able to open up this massive amount of information to then parse it.
Ideally, you would have lots of groups. That's kind of why I was making this startup analogy.
Yeah,
so you would
yeah.
have a proliferation of different groups looking at the data. Like we would basically have to find a way for to make it seriously easy to access so that lots of people could be working on it.
And I also think that developing, so I have a theory of the worlds. It's not particularly interesting or unique. I think that a lot of people have this theory, which is that status is what people chase. Whether you're chasing status in terms of starting some kind of startup that gets sold for $1 billion, or you go into research, and we met people in grad school who were like, I want to have a Nobel Prize one day, and that's why I'm here. And you're like, good luck, buddy.
Those people didn't make it through grad school.
They did not, but they arrived with the intention. And so everybody's kind of chasing status. And we have one form of status that is very apparent in science, which is publishing in a really big journal. Science, Nature, Cell, whatever.
Or professorship, yeah.
Those things seem to be interlinked, right? Like if you're going to be a Harvard professor, you're probably going to be publishing in Nature or Science or whatever. Okay, so like there's this internal academic success status symbol. Is it possible to create a parallel system where there's also status that is not granted by the institutions so that people are able to pursue these sorts of questions and gain status in a way that's meaningful to them without having to interface with the universities? Or are the universities forever going to be the thing that even the people on the outside covet because that's the golden bar to reach? Is it possible for an external society to have that kind of status?
In Europe, as far as I know, most of the research is supported by the state. It's public research because it is very expensive. The state is the only institution that can afford these big amounts. Even sometimes you need to join several countries to build one telescope or to build some instrument. It's huge. There are no private economies that can support this. I know that in US there are some rich people that support some ideas. For instance, I know, for instance, that for a search of extraterrestrial life or these kinds of things that usually are not very supported by the public funds, but there are people who are fond of these ideas and they want to support this idea and they give money. So there are these kinds of enterprises. As far as I know, there is not anyone specifically dedicated to cosmology. And if there were such an association, possibly the mechanism should be similar. As you said before, previously, in the moment in which there is a huge amount of money to divide, you need some controls. Not the first one. Hey, I want some €1 million to build. No, you need some control. You will have some committee just of expert people just to judge who is deserving this money or not. And in the end, you will be doing the same game. No, in the moment in which you are making these filters of science, of quality, you need to put filters because we are too many, and there is not. There are thousands of people doing professional science, and many other tens of thousands which are not professional but would like to have some money just to express their ideas. So we need. It's real that the massification of science needs to have some filters of quality. Otherwise, this becomes chaotic. Even now,
which is why the best you can hope for is lots of different institutions as opposed to one megalithic institution, right? Of course, there's going to be filtering, but there are some alternative institutions. What about, is the Perimeter Institute an alternative institute? Is it pretty?
I don't think
pretty
so.
essential, but I still think that the best you can hope for is people who are doing filtering, but they have wildly different priorities. So there's actual diversity of institutions as opposed to everybody being on the same program and fighting for the same money sources, essentially. When you have different investors, like you have a billionaire who's like, yeah, I'm interested in, alternatives to dark matter. And then you have a different billionaire who's like, I'm interested in alternatives to Big Bang. And then you have just different initiatives. You would probably have a different filtering operation applied to each one of those sets of candidates. And I think that that's kind of the most beautiful thing that we could ever hope for. I don't know if it's going to happen, but it seems like a way forward, at least.
May happen. It's possible in the future, and it's not a bad idea, either with public funding or private funding, a billionaire. It's not a bad idea just to create some space, not necessarily too large, but even 1% or even less than 1%, 0.1% of the research dedicated to cosmology, only dedicated to some alternative ideas, will be enough to have some space of discussion. This will be something. Yeah, I would like to mention, for instance, there was a very brilliant idea some years ago that was the creation of the preprints. Maybe you know the preprints of archive. You know it. The archive was created. First was in Los Alamos in the US in the 1992. And for the first 10 or 12 years, I remember because I was a student in the 90s, it was a totally free place. And you don't need to have any referee, anything. You want to post your ideas of physics in the archive, you go, you submit, and everybody was admitted. However, and this is the point, maybe somebody complained that there were very many exotic ideas. Not many, because I will say that less than 5% of the papers were just exotic ideas. The rest were conventional mainstream ideas. But apparently somebody was disturbed by these crazy ideas coming in archive, and they decided to put filters. This is something that I have not understood, because archive, internet in general, is free. You don't spend money. You don't need to pay, to put. Of course, you have to pay the computers. But just having a 5% more of papers or less, this does not affect. It's not too costly. And moreover, archive nowadays is a monopoly in some sense, that all the physicists need to submit their papers to archive to give some visibility. And most physicists know archive, so it's a very good instrument. The problem is that for some reason it was constrained to have to avoid some topics. So if somebody submits a paper, not published in any journal, and you are not a professional scientist, and you just want to post your ideas in archive, usually you are rejected too. So there is a filter also in archive. This obsession with putting filters everywhere, even in the places where there is no money, because as I said, the archives internet should be free. I think, obeys to criterion of controlling the direction of science. There are people who do not want to diversify the ideas inside. They want some main point and not to make so much noise. They think if you introduce too many ideas in some kinds of problem like cosmology, you create noise, and this distract the people. No, they should focus in what is important, which is measuring the cosmological parameter with this precision and this standard science. Otherwise, I don't understand why. But this is the reality. Before I forget, also you mentioned previously about that the big companies cannot produce so much innovation. This maybe happens in private companies, but it also happens in science also. There are many analysis, not made by myself, by other people that I have read, that they try to measure with some parameters the disruptiveness in the scientific discoveries. Last year was published, it was even published in Nature, maybe you know this paper, and they have analyzed that in the last 40 or 50 years, this level of disruptiveness in the average level of disruptiveness has been going down for many decades. There is more money in science, there is more people, but the papers are less innovative. This means that we are creating a science which is a repetition of many things. We have better data, but there is a repetition. We are doing the same thing that was done by the previous generation, and so on and so on. They are not making many new revolutions in comparison with the amount of scientists that we are. Of course, there are exceptions, but and this applies to all science, in physics, in biology, in everything. You know this paper that I mentioned?
Oh yeah. This is something we talk about all the time. I mean, it not only applies to, it applies to, it seems like, all large-scale organizations of human beings. Like, this is something that happens all the time. It happens with governments, it happens with companies, it happens with scientific institutions right now. And there doesn't seem to be an obvious way around it other than building alternatives, right? Like, other than building a new institution, which will inevitably decay in the same way and become less productive after 100 years or however long it takes. You know, companies, I think, last about, they have a similar lifetime to a human being, basically, right? You can't have an immortal institution. You need to always revitalize your approach, and the only way to do that is to build something new in the shadows of what is old, in order to actually have something that's productive and progressive in the best way of the word, right? That is actually taking a new lens on the phenomenon. And so I think that's fine. I don't know how that's going to play out in the future. It certainly seems like we've all said there aren't that many alternative institutions just springing out of nowhere. It's very expensive. And so I hope that can happen, but history would probably say that usually these things kind of decay before they're replaced by something. They become so ineffective, you know, government bureaucracies eventually, even the longest lived government bureaucracies in China or something, they eventually just become so ineffective that people stop depending on them. And they eventually, you know, there's usually some horrible dark period for a few years. And then,
or 1,000.
No, it's usually not 1,000 years, but let's say 400 years. No, for a while, you know, people try to sort it out, and they're like, well, that didn't work out, so let's try something new. And it doesn't have to be that way. There are revitalizations. There are direct continuums between civilizations and
there are, but
institutions.
there's also this crazy thing that happens where it's like after the fall of the Roman Empire, the whole of philosophy was commentaries on Aristotle for like 1,000 years. And so I'm like, are we just going to be doing commentaries on Gamow and Einstein for the next 1,000 years? It seems not impossible.
Agreed.
If we accept that the only kind of research that is worth paying attention to, yeah, exactly, is the stuff that's in these big journals. But I think that the archive is actually really interesting because I don't know if you guys know about this alpha hive, where a group of, I think, Stanford grad students put together a forum for the discussion of archive papers. And so when an archive paper gets uploaded,
I know.
it still has like the normal page, but this other website is indexing all of the archive papers, and there's now discussion pages where people can show up and they can talk about this research and actually have a community where it's not peer review, quote unquote, in the sense of allowing what gets published or not, but at least you can be in contact with people that are interested in the same questions as you are and reading the same stuff as you. And that seems...
If those questions have been allowed onto archive in the first place.
Does archive...
No, that's what he's saying is like it started off as a free post place, but
Sure.
you cannot just post to it now.
Well,
You have
as
to
long
have
as you have an
institutional-
institutional affiliation.
Yeah, but
Not even.
not yeah.
Not even. I have known some people that professional scientists that were rejected, even if their papers were accepted by some journals. So the papers accepted by some journals and rejected later by archive. So the level of censorship or the filtering in archive has been increased over the last years. The criteria I don't know exactly why they reject, but everything which sounds very polemical, very nonsense in their opinion, is immediately rejected without any review, without not any report, not any peer review. No?
That's creepy and sad.
It's part of this whole institutional paradigm itself now.
Yeah, it's true. I just kind of, that's one less example that I have in the world of things that are working well. So,
I mean, humans are incredibly innovative, and I would not be surprised if the way that we access knowledge in the future is very different than reading a journal article, first of all. Right, there may be all sorts of interactive wiki mode AI.
I imagine just like floppy disk straight to the brain, just uploaded immediately.
Yeah, I don't know. I think that we're in a period of incredible informational reorganization. I think that's really what this whole AI conversation is about, is how do we access all the information that we've had? How do we take all that data from the James Webb and actually make sense of it? And I think the way that that's going to be done as we become increasingly powerful is going to look very differently than the way that it's been done in the past. And so I'm hopeful, at least. And I do think that small groups of people could become empowered with these new tools to come up with incredible conclusions that, if a lot of people are working on these problems from different angles, you might actually get some true progress and some displacement of the old institution in favor of new institutions. I think that's the best we can hope for, is new institutions. Like, humans love something reliable, like an institution that's slow to change and very steady and cold. Like, we love institutions, but we need new ones also. And so I hope, and I think that that's probably our best road forward.
Well, this is one point of view. I'm more pessimistic than you. I think you have mentioned before. There are many topics that we have touched, but you have mentioned that maybe we are reaching some kind of new dark age, which like in the Middle Age, that we are coming back. I think I quite believe that we are in this direction. We have to admit that science it was very successful during the last 4 or 5 centuries in the Western countries, in Europe and US and the Western society. We have produced an incredible intellectual activity. We have been able to understand many things, but this rhythm of producing interesting discoveries and new ideas and disruptive discoveries, and this will be not forever. So we have to admit that not everything is forever. Science has been successful in the last centuries. The fundamental science, I mean, not the applied science. Applied science is another thing. Just making computers, making cars, this is engineer. But just the thing of fundamental science, understanding nature. There are some limits. We have to admit that there are some limits which are very difficult to go beyond these limits. It's not impossible, but they cost a lot of money. This is the question. Now, there is one fundamental reality in physics or in biology and everywhere. The higher is the amount of knowledge that we have in science, the higher the amount of money you need to put to get new truths. So, and we cannot continue this trend of building new telescopes, another telescope even larger, another telescope even larger, and then a particle accelerator the same, because human beings are finite, are not infinite. We cannot grow exponentially. This is like a Malthus, no? The idea that there is a limit. We cannot grow. We cannot create infinite institutes of research. We cannot create infinite devices because our economy, our materials things are already close to the limit. I think in the US, 3% of the GDP or something like that is dedicated to research. And it has been the same more or less in the last 20 or 30 years, has not grown much. In Europe, in Spain, my country, now we are in 1% of GDP, which is not bad. It has grown in the last years, but for a country like Spain, it's quite good. So I think we are quite close to the limit. This idea that we can expand exponentially like animals, like bacteria, yes, it's not possible because the amount of food is finite, and the food here is the money and
and how. But I think it's more how the money is being spent. For me, it's like the same thing could be said about our healthcare structures, right? We had some amazing success early on in the last century in terms of improving longevity and quality of life for human beings through understanding biology. But nowadays, pumping more money into medical technology and the pharmaceutical industry doesn't really seem to be improving people's lives the same way that it was originally promised. It certainly isn't expanding our lifespans in the way that it was hoped. But there is...
America spends the most money of any country on healthcare. And I think that among the wealthy countries, we have the lowest life expectancy.
Exactly. But that doesn't mean that it's the end of the line for life expectancy or for the health of Americans, right? There are ways for us to become more healthy, right? But they don't involve expensive drugs or technology necessarily. They don't involve building more hospitals, right? There's not pumping money into the situation isn't the right approach necessarily.
I'm like, if you spent, let's say, $10 billion on the James Webb, right? So that is over the course of many years, many countries pumping some percentage of their GDP into this project. Okay, great. We've built the James Webb. Now we have two options. We can either say that at this level of funding allocation, what we will do is we will now save up for the next telescope, which is going to cost us $50 billion, and that's where we're going to put all of our money. Or we could say that, hey, how about we put that $50 billion into figuring out how to analyze this data, how to look...
From diverse perspectives.
Yeah.
Which is really amount to constructing like a multipolar institutional structure where folks are attacking it from wildly different angles.
Yeah, because you said this earlier, like we live in this time of faster, hurry, collect more data. Before you finish the previous analysis, you have to move on to the next one. And so you have this complete loss of time to breathe. And so I'm like, if we can allocate money towards giving people time to breathe and think, as opposed to just build progressively more and more expensive detectors, then maybe that would be enough. I think the thing I'm pessimistic about is that that's a possibility.
Yeah.
Because I'm like, now that we've built the $10 billion telescope, surely we must build the $50 billion one. Like,
as long as we look to the government to be the provider.
No, science has become very dependent on the economy. In the past, was not like that. Science was a question of brain. Just you are very intelligent, you think, you dedicate, you have some time, and you produce ideas. Now, we are becoming more and more dependent on the economy. This means that if you invest double of the money, you produce double of the papers. It's exactly like this. You can even quantify it like this. And you make a restriction of money. You cut the funds for some year there is a crisis or whatever. You reduce the amount of people. And the result is that you produce half of the papers or whatever. It's totally proportional. And all scientists will tell you the same thing, all especially experimentalist scientists. Theoreticians is another thing, but theoreticians depend also on experimentalists. But experimentalists say, okay, we have reached the limit. Everything we can do with the CERN, for instance, the particle accelerator, we have already done it. Now, if we want to go to the next level of science, first rank level of science, then we need an investment 10 times higher than the previous instrument. And this has been the trend in the last decades, because we have become totally dependent of the instruments. Our science is being so successful not because we are more intelligent than in the past. No, because we have better instruments. We have better telescopes. We have better particle accelerators. We can read the DNA, also the code, with a lot of technology. So it's the technology that makes science live still. Otherwise, we will be stuck like any other intellectual trend. If you talk with some philosopher, for instance, or you can think, well, what is doing philosophy nowadays? They are doing the same things that 1 century ago. They are not advancing. And why science is advancing so much? Because there is technology. We have computers, we have instruments. But this makes an advantage and a disadvantage. We are so dependent on the technology that in the moment in which you say, hey, you don't have more money for technology, you do your science, a cheap science. So you take your notebook and you dedicate to do your formula and nothing which costs a lot of money. In the moment in which this is produced, most likely there will be a stagnation of the advance in science, because we are totally dependent. And it's sure, according to my opinion, but not everybody agrees, it's sure that we have a limit. We cannot be increasing exponentially the cost of science. So if we extrapolate this increase of science of the last decades, we will collapse in some way because we have no enough resources. Of course, the next step, you say, well, now we have the 10 billion space telescope. The next one, 50 billion. And the next one, we will put a telescope in the moon. And the next one, maybe we will put a telescope of the size of the orbit of the moon, Earth. Yeah, but how many people is going to work to build these telescopes and this technology? You cannot make slaves to the whole humanity only because of this delusion of science. Otherwise, we are becoming like in the ancient Egypt, that the pharaohs building the big pyramids, having a lot of slaves, just building. Well, this idea of sacrificing the humanity for this purpose of science, well, has a limit. And science will tell us which is the destination, but for sure, this will not be forever. We are Western society is exhausted, we have to admit. We have produced fantastic things, but we have not the same intellectual energy than in the past. We have converted all of the business, all of the activities in our culture, science, art, everything, we have converted into a business with the professionalization. And it's true that we can still keep the illusion that we are producing culture, but it's not the same thing. It's not the same quality, and we are totally dependent on technology. If you talk me about other activities, sorry, continue, please.
I mean, I've never heard it put exactly like that. Western society is exhausted because we've turned everything into a business. That's really astute. I don't know if we can. I think that might be a really profound place to pause and think about these things, because so much of what we're talking about revolves around putting the attention and siphoning the attention via the money into these different perspectives and how these institutions get stuck. And it does feel like Western society has gotten exhausted in the last few decades.
Is it just, I feel like everybody's tired. Everybody just wants a break. But I don't know. I like the conversations where we get to the end of our 3-hour window. There's this blossoming of directions that we could go into. And so in my mind, this is a very successful conversation, because I'm like, okay, well, there's all of these different places that we could go and things to explore. And so I think we should put a pin in it for now, because it has been almost 3 hours. And then just plan to meet up again, see how it plays out in the world, the questions that people have. and then see, what new horrors the James Webb finds in the next 6 months or so, and then reconvene and pick up the thread.
Yeah, it'd be fun to talk to you again after new conclusions have been reached, and either more institutional decay has occurred or new institutions are popping up. Either the Dark Ages or the revitalization of the West. We'll see.
What do the next few months look like for you? What are you working on?
I'm working with the James Webb data, precisely. Still with the question of the age of the galaxies, also the angular size. I'm doing the same things that I have been doing always, but with new data. Sometimes I go to some conference also, physics, philosophy also. I have my colleagues of philosophy, the usual activities. I'm also eager to see this new revolution in science, like everybody else. Apart from being a scientist, I'm also fond of science, and I want to have something great again, like this lemma of Trump. No, let's make America great again. Well, let's make science great again, I will say, because everything has become so not the same. The lack of illusions, lack of dreams. Science should be something that make us dreaming about not pure business, not pure getting a position, getting money. No, we should intellectual activities, art or philosophy of science should encourage us to do something just for the pleasure of doing these things. And I also hope this we will reach again these great times of science in which few intellectuals, like in the Solvay conference, sit together and they speak slowly about science. But unfortunately, I think I'm not going to see this within my life. Maybe in the next generation, but the next years, I don't see any change in science. Science will be the same thing with more and more data, more people making a lot of noise. A revolution every 2 days. Every 2 days, you will see in the mass media new fantastic discovery discovered by astronomy. We have a new revolution every 2 days, but these revolutions are forgotten in 2 days also. So they have no effect in the culture. So at the end, as you said, we will still keep talking about Gamow and Einstein, because these are the science that remains, no, the true science that remains. The rest of the things is just fashion things, and the increasing is an incremental science. We are doing an incremental science, the same ideas, but with better data, with more accuracy, and this is the reality today, the incremental science, but not a change of paradigm. There are no conditions, there are no social conditions in our science to create this new change of paradigms. And if it comes, it will come with a change of our society, of our socioeconomic structure. When there is a revolution in society, possibly we will produce a new science with new ideas. But while we have this neoliberalism structure of science in productivity and comparing the science with a factory or a company, we will have the same thing for the next years, I think.
I would put my money on that too if I was a betting man. Yeah, it's been really fascinating to talk to you. You've really helped me get a better sense of the status quo right now inside of cosmology, which is always difficult to get a grip on. I feel like we're talking to a lot of alternative people, and so it's harder to see what's going on the inside. But yeah, I hope this isn't the last time we talk. It's been really fascinating for me. I really appreciate you giving us your time.
A pleasure for me, and I am available whenever you like. Yes, I hope you are very successful with your project of just these talks about science are very interesting.
Well, it makes more and more sense to me each time, so that's the best way I can measure success at this point. But yeah, a lot of people are along for the ride, and we're having a good time. So
yeah, let's do it again soon.
Right.
All right,
have a good
thank
rest
you
of your
so
night.
much.
Bye, everybody.
Well, I'll see you.